So the homework I'm working on right now, it's actually an interesting class. I'm glad I'm taking it because it's something that I need to know, especially for some of these projects that I want to get working on with a lot of moving components. It's called dynamics, so it studies how things move through space and how we can model that and predict that. And that seems like it would be very simple if you take in physics. There's like a whole unit on kinematics, and it's pretty simple, but things get very complex when you're thinking about different reference frames, things doing more than one motion at once. So they might be translating, like moving through space, but also rotating and stuff like that. So that's where this dynamics class comes in. So I'm trying to get through my homework for that. So right now we have this setup where there's like an astronaut in like one of those test chamber things where they test the acceleration, right? So it's set up like this. So there's like a pod over here where the person can be, and it's at some angle with the horizontal, like that. And it's spinning around, and this length is 30 feet, and it gives me the equation for the position so I can find the angular velocity and angular acceleration as well. So I'm going to use that to figure out when it says the person will lose consciousness. So the person loses consciousness at 10 g acceleration. So I've got to find at what time that happens. So I think I can set up like two vector systems. So I'll have vectors. So I'll have my fixed vector system. I usually like to call it IJK. Some people do capital E1, E2, E3. But I'll say I, J, and K. I'll have it set up like that, where I and J are in the plane of my page, and then my K is sticking out of the page, right? And then I can also have, there's like a gnat. There's a gnat like flying around my setup. I can also have another basis vector system for my moving reference frame, and that will be set up as, this time I will use E, so I'll use lowercase er, that's my radius vector, so it points in the direction of my radius at all times. And then I also have a vector that is my angle, so I have my angle vector, my theta unit vector. I kind of drew that poorly. And then out of the page again, we'll have, I'll just call this EK. So those are our vector systems that we have right now. And yeah, I think this should be good. Actually, in this case, I might want to do a different vector system. I'll probably want to have a vector system that, instead of polar, I'll have it in tangential and normal. So I'll have one vector system. I mean, it ends up being very similar. So one vector system, that's my normal acceleration, which will actually be pointed into the board or into the center. So I'll have En, I'll have Et, it's accelerating that way, and then I'll have one out of the board that's like EK or something like that. So those are the vectors I'm going to be using. And so, right, we have, let's see, we do have angular acceleration or angular velocity that we can get. So let's go ahead and get that. Yeah, I am doing dynamics. What is a vector system? A vector system is like your coordinates, like your coordinate axes that you choose. So usually what you're going to be used to, right, is like a 2D vector system. You all have seen this before, where you have x on the horizontal axis and y on the vertical axis. That's a 2D axis system, vector system, because you can now place vectors on here, right? And you have two directions that are already defined, and you can represent any vector in these two directions, right? And so you have unit vectors that tell you the direction. So in the x direction, you'd have a unit vector I with the little hat above it, and in the y direction, you'll have a unit vector with the j hat. So, okay, free tutoring, yes ma'am. So yeah, that's what you get. And so sometimes it's easier to set up one vector system over another. So if you have like a disc or a merry-go-round, for instance, let's say we have a merry-go-round that's spinning, right, with some angular velocity, right? And we have a person sitting on the edge of it. Well, if we were to set, and we wanted to model where this person is, if we wanted to know where this person is, it would be kind of difficult to use our normal XY coordinate system, right? Because in this case, the person is spinning around, so the XY coordinates are going to be changing based on a circle, and that's not easy to model. We can do it. We can definitely do that. But it's not the most simple thing. However, if we set up a different vector system, we can make it very, very easy to model. So, if I instead did my model where one axis always points in the direction from the origin. Here, let me make that more central. From the origin to the person. So, like the radius of the circle, basically. So, we'll call that the r direction. And then another vector that, or another axis that points in the direction of where the angle is going. So, the angle, if it's rotating this way, your angle is going that way, if that makes sense. So, at this point in time, it's pointed perpendicular to the R. So then you have this theta axis that points perpendicular. If you set up this vector system, you see it's very easy to now represent where this person is, because now this person is just always located at R in the R direction. So we can say in the R direction by setting up some unit vector that always points in the R direction. Now this is very easy. And what you'll notice is because we set it up this way, our vector coordinate system, it actually rotates with it always rotates with our rotating merry-go-round or rotating disc. And that's why it's easy to model where this person goes, because this coordinate system is moving with our person. So relative to each other, they're not moving, if that makes sense. So I hope that makes sense. And then there's this really cool thing you can do with the vectors that allows you to easily transpose the position or the velocity and acceleration inside of this r theta coordinate system to the fixed rectangular coordinate system that we talked about before, the xy. So that's what I'm working on in my problems right now. So I gotta get that figured out. I have until 11:59 p.m. to get that done. All right, so like I said, our position we'll say is r, and so that's going to be the 30 feet in the ER direction. And so I need to get this derivative. That's important. But the cool thing about this derivative is our radius is not changing. So the derivative of this in reference to time is just 0. So that makes that easy. And then I also have an equation that gives me my angle as a function of time. So I can write my angle theta is equal to 4 times t plus 30 e to the negative 0.03 t minus 30. This was just given to me in my problem, by the way. I didn't figure this out. It just gave me this. So now I can get the derivative of this as well. I'm pretty sure this theta is also a vector. Or not in this case, actually. So the derivative of 4t is going to be 4. If I distribute this 4 over here, you get 120 times negative that number. So I don't want to try and do everything in my head, so let me get my trusty calculator. I love this calculator so much that it's the TI-89 titanium. This thing is good. So let's do 120 times negative 0.03. Okay, and we get minus 3.6 e to the negative 0.03t. And then 30 goes away. So this is our angular velocity. And now that we have that, we can get our velocity in our normal tangential reference frame. So I'll just call this n, I guess. Reference frame n. And so this expression is always this. R dot times ER plus R times theta dot E theta. And we already said that R dot is equal to 0. So boom, that goes away. So now we're left with, not V dot, just V. V is equal to 30, because 30 is our R, times this expression, so times 4 minus 3.6 e to the negative 0.03 t. And what am I forgetting right now? Times e dot theta. Okay. we need the acceleration. Whoops. All right, so let's get one more level of derivative. So we don't really need v, but it was cool that we got it. So actually, what we want is a. So we'll write in our a in reference frame n is equal to r double dot minus r theta dot squared er plus r theta double dot plus 2 r dot theta e theta. So turns out we need theta double dot. So let's get that real quick. Theta double dot is equal to, what is that times negative 0.03 again? Whoa. Okay, yep. So we get 0.0 or 0, whoops, 0.108 e to the negative 0.03t as our theta double dot. Now we have this big expression for acceleration, and we know that r dot is equal to 0, so this goes away. This r double dot is also going to be 0, right? So now we're just left with a of n equals r theta dot squared er. So this is our normal component, and then we'll have plus our tangential component, which will be r double dot e theta. All right. So we can now just plug stuff in. So we got 30 30 times 4 minus 3 point e to the negative 0.03t squared er and 30 times, what is that called? Theta double dot. There we go. 0.108 e. There we go. Okay. We're good. Man, I was having like a brain fog for a second. Oh, and then we have e dot theta. And it said that the person passes out once they reach an acceleration of 10g. So what we can do is we can set both of these equal to 10g. Yeah, we can set both of these equal to 10g, and our g has to be in feet. So I think our g is 32.2. I don't remember it off the top of my head, unfortunately, chat. I usually am used to 9.81. Yeah, 32.2. So we'll say that each of these are equal to 322, and then we can calculate the time for this to 3 significant figures. So what we got was 53.4714 seconds. So we'll put 53.5 seconds. That's what we get as our time. So we'll say t equals 53.5 seconds.